Well, it's a great pleasure to welcome you on the second day of the FM week. And it's even a greater pleasure to introduce the keynote by Sir Tony Hoare. This is jointly organized by 5 events in FM, Lobster, MCP, PPDP, RV, and UTP. So all these events synchronized so that we have a very nice audience to hear to Tony's talk. As Lobster, RV, and UTP are starting today, we will take these 10 minutes before 9 o'clock just as kind of opening remarks for this conference. So I will start talking a few things about UTP, and then this is going to be followed by the others that will talk about RV and Lobster as well. So Pedro, Ribeiro, and I are organizing this very special edition of the UTP that is dedicated to celebrate the 85th birthday of Tony Hoare. And also we can consider that we are celebrating the 50 years of one of his very classical papers on an axiomatic base on for computer programming. So it's a really special edition of this UTP event. So Pedro and I would like particularly to welcome the UTP participants. In this edition, we have all the papers were invited, and so we will have presentation of the very highest standard. And this presentation went through a very friendly review process. And so we would like to thank both the authors and the PC chairs for their very kind and dedicated work. So the program, I'm sure, is to be very exciting. The attendees will be delighted with all the talks. We'd like to also to thank Ana Cavalcanti, Jim Woodcock, and Ribeiro for trusting on us this organization of this particular special edition of UTP. And also we'd like to thank José Nuno de Oliveira, the general chair of this event, for the very, very nice work he's doing, as you might have already noticed. Finally, we'd like to thank Springer for the usual support with the proceedings. And then before Pedro introduce Tony to us, I'd like to give the word to Maurizio so that he says something about Lobster. Maurizio, okay. And then
Yes, hello, good morning. Just a few words on behalf of the Lobster organization. Of course, also for us it's a great pleasure to be here to celebrate Sir Tony Hoare's birthday and to listen to his talk. So it's really a great pleasure. And Lobster is a very small conference, which nevertheless has a long tradition. This is the 29th edition. And as the title suggests, it's a quite specialized conference. So Lobster stands for Logic-Based Program Transformation and Synthesis. Nevertheless, as Lobster has traditionally been opened to other fields, and in the program, indeed, we have sessions on static analysis, constraint programming. There are also some new trending stuff like blockchain technology. We have 3 invited speakers from different fields, Naoki Kobayashi, German Vidal, and John Gallagher. So I think we'll provide 3 very interesting invited talks. And just a few words also from my side to thank really José and all the FM Week team for the excellent work that we've been doing. Even in preparation, it was very smooth for us to interact with them. So thank to all of them. And the last operational announcement, for those who are interested in attending LOBS, please be aware that the conference will be on the next side of the main street. So please have a look to the instruction that you have in your bag. Thank you.
Good morning. A very warm welcome from Leo Mariani and from myself. My name is Bernd Finkbeiner as well. We're chairing RV 2019, the conference on runtime verification. The official opening of RV will be tomorrow when our presentations of regular papers start. Today is our tutorial day, so we cordially invite you to come to our tutorials. There are two tutorial tracks today. In the morning, we have a tutorial on hyperproperties and one on specification robustness. So they are in two separate rooms in this building. And in the afternoon, we have again two tutorials about stream-based monitoring and about runtime enforcement. All right, thank you very much. See you there.
Okay, good morning, everyone. I have the honor to introduce you our distinguished invited speaker, Sir Tony Hoare. Tony Hoare's highest academic qualification is an MA in classical grades from Oxford. He studied Latin and Greek, both the languages and the literature. This was followed by ancient history and philosophy. It was philosophy which stimulated his interest in logic and the foundations of mathematics. It also stimulated his interest in computers as a tool for studying the philosophy of the mind, and in particular human intelligence. He earned professional qualifications as an interpreter of Russian and as a statistician between 1958 and 1959. He exercised his Russian as an intern at Moscow State University, 1959 to 60, and on many subsequent visits to the Soviet Union or Russia and to Armenia. He holds 13 honorary doctorates from the United States, England, Ireland, Scotland, Warsaw, Spain, and Russia. His first job was in the UK computer industry at a small computer manufacturer, Elliott Brothers, you might have heard, where he held the posts as programmer, chief engineer, and researcher from 1960 to 1968. He led a team, including his wife Jill, in implementation of an early compiler for Algol 60, which stimulated his interest in formal language definition. He then led a much larger failed project to write an operating system, which stimulated his lifelong interest in concurrency. He then applied for the chair of computing science at Queen's University in Belfast, and to his surprise, he was appointed from 1968 to 1977. He set up the university's first undergraduate degree in computer science, at first joined with mathematics. He selected program verification as a topic for his first academic publication and for his entire subsequent academic research career, spanning 32 years. He reckoned that verification was a topic not likely to be of interest to industry until after he had retired. So he would never have to compete with more generously funded industrial research, and his prediction was quite correct. He left Belfast with regret to return to Oxford University as Professor of Computation from 1977 to 1999. There he learned denotational semantics from Joe Stoy and domain theory from Dana Scott. And after 2 years of pure research, he set up a master's degree at Oxford in computation, and much later an undergraduate degree, at first joined with mathematics and then with engineering. His first retirement job was in Cambridge with Microsoft Research from 1999 until 2017, where he stimulated an international Grand Challenge initiative in verified software. Since his second retirement, he has been an unpaid visitor at Microsoft Research and an honorary member of the Cambridge University Computing Laboratory. His third retirement will be after giving this lecture. So let's hear from Tony on a calculus of space, time and causality, its algebra, geometry, and logic. Thank you.
Well, thank you very much for your elegant introduction, and thank you all very much, my friends, for coming to listen together to this lecture, which I've been working on quite hard for the last 6 months or so. And thank you to my co-authors too, both of whom are here. Where are we? I'm going to start by mentioning a problem that is central to the study of the unifying theories. The motivation for the development of unifying theories is something that Christopher Strachey called the variety of programming languages. Today, large systems are built of programs which have been assembled over many centuries, many decades, and they're used together in the same software system. And if you wish to ensure the structural integrity of those systems, which is a more directly important problem than functional correctness, you need to have some common framework in which you can place all these languages and show that each individual component is structurally sound when connected in the particular way to the other components. So it's a major conceptual engineering job to maintain control over the structural integrity of, well, the structural integrity, of course, includes the interfaces between the major components, because an error at an interface is, first of all, much more difficult to debug, and secondly, likely to be far more structurally damaging to your software as a whole than you would ever find by unit test. A unit test may be useful for functional correctness, but for structural correctness, we need to turn to a more unifying approach that covers these languages. Now, the languages are not the ones that have grown up to serve particular needs on particular hardware configurations and in particular applications, and to embody particular functional paradigms. So the secret of one of these special purpose languages is it finds some principle of design, a combination of a paradigm, an application, and a hardware implementation, of which there are many general purpose components and many robotic components involved, which solves a problem that could never be solved by a general purpose language. And I've given some examples on this slide. And in the end, each component of the system should ideally be designed, tested, and proved in a uniform programming environment, which is based on the fundamental principles that we're very familiar from in the real world, causation, space, and time. Well, here's a brief summary of some insights that I've gained on my investigation. Semantics has been bedeviled for many decades by a divide between those who start with the concept of a state, machine state, and those that start with events. And these two fundamental concepts can be the subject of infinite discussions among fundamentalists. I'm not a fundamentalist, and therefore I'm willing to accept both of them, like a polytheistic religion, as equal partners in my foundations of the subject. So states are potted histories of recent events that have happened to evolve that state, and events can be defined as changes in the state. Now, I will concentrate on events because causality is a relationship between events, not between states, and I hope to show you how I can construct states out of causal relationships between the before and after events. Now, space and time are orthogonal axes onto which causality projects. An object can be represented geometrically as a space coordinate whose points are collocated events. They all occur in the same place in space, in the same location of memory. A transaction is a time coordinate whose points are simultaneous. They all occur at the same simultaneously at the same virtual time. Well, virtual time doesn't have to absolutely correspond with the real time of any particular execution. It is just defined in the way that atomic events are defined, that it's impossible to perceive the state of the machine in which some of the events of the coordinate have occurred and some have not. So causal relationship holds between adjacent events on each coordinate. So each event in a vertical coordinate depends on being caused, or at least being preceded, by the previous event on the same coordinate. And in the case of other causal relationships are used to pass messages between threads, they also use the causal relationship to indicate that the output cannot take place, the input cannot take place before the output. And if you violate any of these conditions, you will violate the concept of causation, which is a fundamental concept of physics and punishes those who violate it. One of the possible violations is a causal cycle in your program, which is punished by a deadlock. It doesn't actually occur, but only at the expense, only by avoiding executing any more of the program which has called it into existence. So, in general, I think I would like to summarize the similarities between computing and other branches of science. Language of computing is defined by terms, represented often by abstract syntax trees, with the semantics in the real world. Certainly for natural science, the semantics of concepts like energy and distance and time and speed are actually something you have to point to the outside world to understand what they mean. I'm going to apply this same principle to causality, space, and time. No definition of it, you all know what I mean. And furthermore, they all use some kind of pre-ordering relation to express their primitive judgments. We call it refinement in programming, implication in logic, and deduction, as described on this slide. So it gets down to business. Events and traces. We let events be the set of all potential events that can occur inside or at the periphery of a computer system which is executing any of its syntactically correct program. A very sparse space, a very infinite space, a very mathematical space. Very few of the events in the mathematical space will ever occur. The trace of each phrase in a structured program records a single execution of just that single phrase. It may contain 0 or more executions of the same subphrase in the program, for instance, a conditional or a loop. So we let the TR, traces, be the set of all such traces expressible in a given language. So the traces are expressed in the subset of the language which omits all forms of choice and repetition, and it's this form that excludes non-determinism, conditionals, and loops and recursions, but it includes the sequential and concurrent execution of its component phrases. So sequential and concurrent composition are the primary operators in an expression which denotes a trace. So, since we're dealing with syntactic objects, I will define them by a calculus, normally expressed in Backus-Naur form on this summary slide. 2 operators, one expressing sequential composition, the other expressing concurrent composition of the phrases which occur on either side of the terms that occur on either side of the operator. And you all understand what concurrency is. It's the same one that you see in the real world around you. So, in the trace, each occurrence of a basic command, each execution of it, is drawn as a leaf of the program tree, each of its, and each phrase of the program is drawn as a node. It's decorated by the operator which composes its arguments and branches, and the same operator decorates nodes of each trace that executed the phrase. The important function which links a trace to its program is the execution function. Trace T is an execution of the function of the program P. Is a primitive concept. If you're a programmer, you have to understand what this relationship is and be able to see what kinds of traces can be evoked by your program and what kinds of program could have been the trace could have been an execution of. So a set of traces corresponds to one program in the language. So I'm going to use P and Q to stand for nodes or terms in the either a trace or a program, and sequential composition is now a phrase in the trace or the program. And I'd like to give tribute to William of Ockham, who was actually a friar at the college I studied at in Oxford, studied Great Sat, and is better known as the author of Ockham's Principles. You shouldn't multiply your primitive concepts unless you really need to. So here's an example of an abstract syntax tree. Its major connective is a semicolon. Its two minor connectives are concurrency, and I've drawn the picture on that slide. So there is a vital function, which I will call ev, which maps every node and every leaf of the tree to a set of events. This is a functional representation of the syntax tree, and we can compute the set of all the leaves of a tree by the function shown on this slide. The symbol 1 stands for a program that actually evokes, has no event in its trace. It does nothing. The K is a leaf of the tree, and it is its unit set gives the answer that you want of the set of all events contained in that unit set. The sequential composition and the concurrent composition are just the disjoint union of the events in each of the operands. So here's a very important concept which is a little bit technical and maybe a primary driver of the methods that I'll be using to relate traces, events, and programs. The separations of a node, the sequential separations of a node, which I call SSEP, measure give you the set of pairs inside the abstract syntax tree, which are connected by semicolon as opposed to concurrent composition. So every pair of every pair of leaves in the tree is separated either by a semicolon or by a concurrent composition. In fact, it's the one that occurs at the meeting point between that leaf and the root of the tree of the two different operands. So if the tree meets when it first meets at a point, look at which operator decorates that node of the tree, And if it's semicolon, that pair is a member of is a sequentially separated pair. And if it's a concurrent operator, it's a concurrent. And here we have a little example of which I've given before. I think maybe forget about the inequality between those two expressions. The first line of the slide gives the set of pairs that are sequentially separated, which are, as you see, the Cartesian product of the leaves PQ and the P dashed Q dashed. And I've got a misprint here. I'm not going to use this slide again, so I won't explain what the misprint is. The definition of concurrent separation just is the same definition, except that the defining operator is a concurrency operator rather than a sequential operator. And every pair of events in a trace is going to be the disjoint sum of concurrently separated pairs and sequentially separated pairs. So the exercise is define a partial function which is the inverse of S sep. It's of course partial because the function that it is an inverse of is not a surjection. You can look up these exercises in the lecture notes on the website of the conference. So now let's get on to my favorite subject, algebra. I will talk about refinement, the axioms of concurrent Kleene algebra, programs, lifting to sets, and additional operators for time and probability. Refinement is defined as a comparison of the sequentiality of P with the sequentiality of Q by looking at all the pairs that are separated. So P refines Q if the separations of P are a subset of the separations of Q. Every pair that is separated by a semicolon in P is also separated in Q, and the events are equal. And the equivalence is defined in the normal way of defining an equivalence from a preorder, which is by mutual domination in the comparison. So we can now compute an example in which the separations of the left-hand side of the example are actually equivalent to the separations of the right-hand side. The calculation you could follow in the slides, which are also on the website. Just two steps. And here are the axioms of concurrent Kleene algebra, all of which can be proved by the same technique that I described on the previous slide. So the concepts of C sep and S sep are clearly very important in proving that these axioms actually describe the syntactic forms that I have on my as my foundation of the study. I'm need to take my watch off. First of all, we have defined the refinement operator so that it's a preorder. Furthermore, most important property of all the operators that I will be treating is that they are monotonic, or as I prefer to call it, covariant. When you make any of their arguments more refined, you refine the whole expression if you leave all the other arguments unchanged. So this is a fundamental principle of many branches of engineering and science, where if you upgrade a component in a product that already exists, you will only upgrade the product, you cannot degrade it. Or you might leave it the same, it might have no effect, but it's not allowed to reduce or change the performance of the product except by improving it, by refining it. The unit law is very trivial, and the interchange law follows very directly from the definition of the ordering operator. And this, I would say, is the fundamental principle of concurrent computing, because in combination with the other axioms that I've shown you, it authorizes selective sequential time sharing, usually called multi-programming, to match a program efficiently to the number of cores which are available for its execution. This fundamental principle has been proved to be true of Turing machines. In fact, according to my definitions, it's true of the real world, so that shouldn't be surprising. But it has been essential to the development of the marketplace in software, concurrent software, that you are able to run a program on a computer that contains either less or more processing elements than you have actually called for in the program. Without that, you couldn't transfer your libraries into the common marketplace for processors of all different sizes. And so you would have to write separate libraries, complete libraries for programs, well, shall we say, between 6 and 10, which do not use more than 6 processors, and you would not be able to, and others which will not be efficient on ones with more than 10 processors. And we would just not have the software marketplace that has delivered all the software that we use every second of every day in our lives in the modern world. A very important principle. Fortunately, it's easily proved in the calculus. So, a program has many traces. The set of all possible traces of the program, all valid traces of the program, gives you the definition of the programming language. If the programming language definition ascribes tells you how every program written in the syntax of that language will behave, provided that the result is an okay trace. And I'll come and describe, I've already given you an example of a trace which is not okay. A trace that contains a causal loop is not okay, and it's not going to obey this law or obey the laws of concurrent cleaning algebra. In fact, the hardware designers have told us that if we make a programming error in the program, the whole program is meaningless. It's not okay, and the optimizer can do whatever it likes to, as it were, optimize that program into something that behaves completely differently. People who are familiar with relaxed memory will be very familiar with this idea that you've got to get everything absolutely right or all hell breaks loose. Dijkstra was the originator of that idea, who felt that an incorrect program was not worthy of his attention. Well, there were many features of modern programming practice of which he disapproved. Now, the lifted sets are also a concurrent cleaning algebra. The proof is tedious. Formal proof is tedious, but the the essential reason why the theorem is true is because all the axioms are linear, in the completely formal sense that each free variable in each axiom occurs exactly once on each side of the refinement operator. If you go back to that page in the slides, you'll see that all the axioms satisfy that property, and all the proof rules will satisfy it, will preserve that property. And this was pointed out to me by Bernhard Müller. So now let's try a slightly more ambitious language in which there is a concept of time, in which time could be either real time or virtual time. The axioms should be the same because the purpose of virtual time is to simulate real time. So I introduce a primitive like SSEP, which maps traces onto the duration of their virtual execution. It's a numerical figure which gives you the length of an interval in possibly virtual time, simulated time, or possibly real time if it's the world. The duration of P semicolon Q is equal to the duration of P plus the duration of Q. You can't start Q until P has ended. Duration of P parallel Q is equal to the maximum of them. You can't actually do the pair of them faster than you can do the slower of them. And the duration of a new primitive command, a leaf, is simply the numerical value of its parameter d. And that causes the program to be delayed for execution for an interval of d times. And that's the end of my axiomatization of time in a trace. Time in a program is, of course, the set lifting of that. There is nothing more. I have designed you a special purpose programming language in one slide. Probability. Oh, very complicated subject. This we need a slightly more complicated thing. We need to take a pair of traces as an argument, of which one of them is actually a subtree of the other. We want the probability of R given that you are already committed to executing M. So the probability, if you're already committed to executing M, by calling this command, within the M, within the execution of M itself, then you're already there. The probability is 1. If you are computing the probability of P semicolon Q, which is the same as the probability of P, and equal to the probability of Q, and the same for the parallel composition in the last. This is because a trace contains a complete execution. There's no such thing as an interrupted trace of P semicolon Q. It contains all the events of P and all the events of Q, and therefore the probability that you are going to be in one of them is equal to the probability that you're going to be in the other. And then finally, if we have a probability statement, which I will draw with the probability indicated by the variable y inside these curious brackets, invented by LaTeX, I think. Tim, yes? Well, the formula is well known in probability. It's the probability of y times the probability that you will get to P, and 1 minus y times the probability that you will get to Q, because those two are exclusive. And the probability of exclusive events is the sum of the probabilities of their argument. And so the operator intuitively selects P with probability y and Q with probability 1 minus y. And to check that you've understood that, supposing y is restricted to being either 0 or 1, then the phrase that I have drawn as a probability phrase at the beginning of the next line means that if y equals 1, you execute P, and if y is equal to 0, you execute Q. So, exercise, what are the properties of this if you could regard it as a parametrized operator? And which of these properties are preserved by the actual probability statement where y is allowed to vary between 0 and 1? Oh, we're almost up to the level of Simula 67. It's a very influential language from which all object-oriented languages have been derived, and the basic concepts of it are included in many other languages. So let me introduce now the subject of causality. It's a relation between events in the same trace. You don't go between traces with causality relations because the traces are all completely alternative to each other. No event occurs in more than one trace. We've got plenty of events there. Remember, I told you it was an infinite set, and so there are enough events in mathematics to cover all cases without needing to duplicate or reuse. And K causes L means that K was a prerequisite for the occurrence of L. Slightly unusual definition. It's because the causality that we need is a necessary causality. You want to be able to reason backwards from an event and say, if this event occurred, then this other event must have occurred earlier, or possibly simultaneously with the caused event that we're interested in. So let me restrict the concept of causation to events which are separated by semicolons, which I can do algebraically by taking the S-sep relation, which are a set of all pairs that are sequentially separated, and intersecting them with all pairs of events that are causally related, and it gives me those that are sequentially related. So in my interpretation of the meaning of this, as it were, the real world that occurs inside, computers are part of the real world, so I will be talking about them too. The events K and L occurred in the same location at different times. You're not allowed to do, the same object is not allowed to do the same thing simultaneously, two things simultaneously. That's the definition of an object. That's the definition of an event, which we can axiomatize very shortly. So of course, this concept applies to the real world as well. But in the heap, it describes object-oriented programming. We will need to write axioms which say all events in the life of the object are linearly connected by a chain of sequentially separated events. And I can tell you, the first event of the chain will be the allocation of the object, and the last will be its disposal. End of definition of allocation and disposal. No indication whatsoever of how an implementation is proposed to use garbage collection or any other method for actually collecting it. We've completely separated that problem from the mathematics of understanding what the purpose of allocation and disposal is. And that is described to indicate the first and the last events of an object. Concurrent causation is similarly defined, but in this case we do allow a pair of events to be mutually causative, which means, according to my informal definition of what necessary causation means, that they occur simultaneously. And one cannot occur until the other one has. Now this means that in our familiar interpretation of the calculus, these sets of events at a horizontal coordinate, a chain which is connected by simultaneity is called a transaction, or sometimes an atomic event. And the definition of the atomic event will be just like that of a Petri-net transition. The principle of an event is that nobody ever sees the state of the machine when some of the events have occurred and others have not. So if our horizontal coordinate is drawn as a horizontal line, and the vertical and the causal coordinate, the objects which perform actions inside this transaction, are drawn as a vertical line, we'll put a blue blob to indicate that the event at the tail of the arrow has occurred, and therefore we have a token on the line which will eventually cause the transition to fire. The first diagram, it cannot fire because not all the incoming arrows have blobs on. They're not all ready to occur. When they are all ready to occur, they all occur simultaneously, and any that are on the same line will, all of the outgoing events now carry the token, and clearly on the rightmost of the events on this series of pictures, the event on the rightmost coordinate is actually passed through the transition, and probably the value of the object has been changed. And the actual value of the object transmitted by a causal link can be written as a label on that link. It tells you, in this case, what the value of the object is between the occurrence of the tail event and the head event. During that interval, the object retains the value that is written on the token. Now, there is a third kind of message which does not require simultaneity or, a horizontal linkage which does not require to be symmetric, and it's possible to communicate the information by an input and output instruction, in which the input and output are indeed occur simultaneously, as they do in Milnor's calculus, CCS or CSP. And this arrow carries a synchronized value from the tail event to the head event. All such communication arrows are not symmetric, and all the transaction arrows are, of course, symmetric. And so in relaxed memory, a transition would be called a fence. A fence is, in racing terminology, a fence which all the horses must cross simultaneously, or none of them can. Bit of an unconvincing analogy, I think, but it certainly illustrates what a fence is in relaxed memory. So now we have a coordinate system, a two-dimensional coordinate system, in which the coordinates representing objects in the same orientation are parallel, in the sense that they never meet in a point. No event requires simultaneous participation of two objects. If you want that, you can get it by having two events which are synchronized. So we preserve the regularity of the two dimensions in spite of the synchronization. The coordinates in different orientations, that is the horizontal and vertical, the objects and the transactions, may meet in at most one point. And every point, every event lies at the intersection of two orthogonal coordinates. And this is turning now from a sort of balance between Euclidean and Descartesian geometry, which seems to be very relevant. The thing to remember is, as always in mathematics, the space is very sparse. At most points and at most times, no interesting event occurs. And what we're interested in, what we want to do, is to describe the interesting events and ignore all that enormous surrounding space, which only provide a framework for the existence of the points, but the points are not actually all present. So here's a fragment of a diagram drawn in this Descartesian and Euclidean geometry, where the heads of the arrows indicate events, gaps indicate no event at this intersection, double-headed arrow, well, I suppose I should really point to that. No event there, an event there, it's a termination event, if you remember. The event there is quite a normal event occurring simultaneously with another event, and with the other events on this line, which include an input event for this object, output event for that object, and that is not a symmetric relation. So now we come to the important topic of violation. Everything that I've described so far is purely syntactic. And you could criticize this, but it has a very most important result algebraically, that the model that we have drawn is purely, is what are called an initial model. It is a model that every other model is an abstraction of. So, and this unique up to isomorphism, of course, defines the canonical model for this axiom system, and it's very useful to know. They will all be syntactic, essentially syntactic. Well, they are constructed as purely syntactic in terms of the terms of the algebra concerned, and we've just followed that tradition. So, undefined. Remember I brought OK into my definition of the traces of a program. I'm going to define that now axiomatically. The implementer of a programming language is responsible to avoid producing a trace with any undefined operation. Instead, it must execute some non-deterministic alternative which has been provided by the same program. So choice in the program must be exercised to avoid undefinedness. This is an angelic form of non-determinism in the technical parlance. And its most obvious example is a program which violates a compile time check. Compilers these days have complex type systems, and in fact a lot of the special purpose languages are specifically designed to enforce more rigid type checkable facilities that could not be provided in a general purpose language. It's the absence of the generality that enables the special purpose language both to be easier to prove and to be implemented more efficiently. And in many circumstances where the application is known, it is possible to design very much better languages than the general purpose languages which we teach to our students. So, on slide 17, I used the word OK. Here I've defined OK just simply as the negation of being undefined. This must be distinguished from a different kind of error which is made by the programmer. Something like zero divide is considered as a programming error because there's no way in which we can type check whether, certainly in an object-oriented language, whether the result of a division is going to be zero. A null reference fetches. If you look at the manual of a modern programming language, you will see many pages of tables of errors which the programmer must avoid because the compiler is not going to help him to do so. Our debugging version of the implementation must detect these errors at runtime. I'm very glad to welcome here the members of the RV conference. They play an essential role in detection and removal of this kind of error, which can't be done by a compiler, and whose absence cannot in general be proved even by a proof system. In order to trace where an error where to correct an error, a trace produced by a debugging compiler should contain the causal relationships between the events that it displays to you. It should not be a store dump. It should not be a stack dump. It should be a history dump that tells you what happens, what are the events. The event is the primary thing that you are interested in changing when you make a programming error. And you want the display system to show you a causal tree, so enable you to chain back from where the error is first detected, perhaps by an assertion, back to a place where you might profitably prevent the error by avoiding its cause, necessary cause. Any necessary cause may cause the error to be avoided, and you are allowed to choose which necessary cause to attack. So if the person who wrote the program is now on holiday, maternity leave perhaps, then you don't bother to look there for your correction. You look in some other place for correction. Even if that's where the error really occurred, you don't have the power to change it at that point. or if it's from legacy code, which nobody can understand, similarly, you don't change it, you change something else. It's called a workaround. Do we teach our engineering students, our software engineering students, the vital engineering concept of a workaround? This is a good place to bring it up. So now, using the concept of an error, I'm going to define you some alternative definitions of what might be meant by the operators of sequential and concurrent composition. Here, I have a definition of a sequential composition which requires the no event of the second operand occurs before any event of the first operand. So now they must all be sequentially composed, and there must be no causal relationship that goes backwards from Q to P. Such a causal relationship would make this impossible to implement. And if this is violated, this is an implementation error. The implementation error has to preserve this kind of sequentiality, which is extremely useful in a relaxed memory, for example, because you've got to do this to avoid some very strange side effects called thin air. Well, except that the engineers who invented thin air, I'll come to that in a moment. So here is a definition of, I think I'm being given a very gentle hint, and level. Concurrency in CSP, I wish to define that by saying the first line of this definition, which defines the operator of concurrency in CSP, is that there must be no deadlock. The arrow star is the general causation, a causal chain, which cannot begin and end in 2 points that are sequentially separated. Because sequentially separated things have got to be separated in real time. And any such occurrence would be a causal cycle. And if the trace contains a causal cycle, the person responsible is the programmer. And that's indicated by the erroneous condition. Here I have a different objective. I wish to ensure that there are no cycles by ensuring that there's no causal link between the two threads at all. This defines the interleaving operator of CSP, just as the previous thing defined the normal sequential composition of CSP. So, assertions are written in programs. Assertion errors are indeed programming errors. Presumption errors are implementation errors, because you write a presumption when you want the compiler to prove that that presumption is going to be true, that the compiler may indeed use assertions in the other parts of the program, because right. Huh. I get a lot. I hope I've managed to visit points which are of interest to members of attendance at all the strands who so kindly joined together to listen to me. And now I get to the point of the UTP, which was the conscience that originally invited me, of course, to celebrate my 85th birthday with you, all my friends, on this lovely occasion. Thank you very much.
Okay, have some. I saw you had choice for your calculus.
Yes.
I wondered, you talked a little bit about angelic non-determinism. Do you think that's something that could be extended to feature as part of your calculus?
I use the word angelic non-determinism as an analogy, which has been used quite frequently in the past. The important thing is to distinguish two different kinds of error, which I have described as programming error and implementation error. Being a programmer, I assume that there's no error in the implementation. And therefore, I'm not interested in traces which contain an implementation error, only in ones that contain programming errors. If I were a compiler designer, I would make the reverse choice. I would not be interested, primarily at least, in testing how my compiler deals with incorrect programs, because I'm allowed to deal with it in any way that I like. And therefore, the implementer welcomes the demonic non-determinism that the poor programmer has to suffer from. Keep the two distinct, and the main part of the definition of your programming language will consist of lists of errors that either the implementer or the programmer must make. This is the contractual semantics of your programming language, and this is real semantics. It's not semantics. It's not anything else. It's telling you what you've got to do. It's morality more than semantics. Who's responsible? So programming language is a contract between the programmer and the implementer, and both sides have different responsibilities, which are described in quite a lot of the 2,000-page manuals that describe modern programming languages. Thank you very much. And thank you as chairman of the session.
Questions from the audience? We have time for one more question, if anyone has one. No?
I have to thank the chairman for both reminding me of the time and for asking the only question that you will ever hear. Thank you very much.
Thank you, Tony. I think we're almost on time, so let's thank Tony again. Thank you very much.
So